welcome to 4.6. Today we're going to talk about directional derivatives. So let's start with a review of the gradient vector. The gradient vector is the vector formed by taking the partial derivatives of f. And in this case, I have an example where f is a function of two variables. And so let's just do a quick example here. Find del f, it's pronounced del f or gradient f, for tangent inverse of y over x. So del f at xy is the vector. I want the partial derivative of this function with respect to x. And so in the denominator, I want 1 plus the argument squared. And in the numerator, for tangent inverse, I want the partial derivative with respect to x. So if we think of y over x, I'll do my scrap paper over here, y over x as yx to the negative 1. When we take the partial with respect to x, we get negative yx to the negative 2, which is negative y over x squared. So that's what I'm going to put in the numerator, negative y over x squared. And then for the partial derivative with respect to y, it's a little easier. Again, the denominator is 1 plus y squared over x squared. And the numerator is just 1 over x, because that's a constant with respect to y. All right? And let's clean that up. It's a complex fraction. We're going to take both of these fractions and multiply by x squared over x squared. X squared over x squared. So the first one becomes negative y over x squared plus y squared. And the second one becomes x over x squared plus y squared. So pause the video, make sure you follow that. Multiplied by x squared over x squared. All right, and then del f at 2, 0, I just plug in 2 for x, 0 for y, and I get 0, 2 over 4 is a half. All right, we can use gradients to find directional derivatives. Directional derivatives are a generalization of partial derivatives, but instead of holding just y constant or just x constant and looking at the rate of change of the function, we're allowed now to let x and y both vary. So down here in the xy plane, x and y can both vary maybe in the direction of u. And then the directional derivative is the rate of change of f in that direction. And so the formula for the directional derivative is simply del f dot u. The important thing is that u has to be a unit vector. And a special case is if u is one of the standard unit vectors, then you're going to get back to our normal partial derivatives, f sub x, f sub y. All right, so let's do an example. And in this example, notice how it's phrased. Find the derivative of this function at this point in this direction. So you're given three things, a function, a point, and a direction. So first step, we need the gradient. Del f at xy is equal to partial with respect to x, e to the y, and then when I take the partial with respect to x of cos xy, I leave the inside fixed, so leave a space. The derivative of cos is negative sine xy. And in front, I'm going to multiply by the derivative of the inside with respect to x, which is y. So I get e to the y minus y sine xy. And then partial with respect to y is simply x e to the y. Then I'm going to do the same thing, except I'll get negative x sine of xy. Okay, so now I need del f at the point in question. P is 2, 0. E to the 0 is 1. And sine of 0 is 0. So first component is 1. And the second component is going to be 2. Okay, now I'm going to let u be a unit vector in the direction of v. So I have this direction here, v, but it's not a unit vector. So u is going to be v over its length. And so over here, let's just find the length of v. That's the square root of 1 squared plus 2 squared, which is root 5. So this is going to be 1 over root 5, 2 over root 5. All right, and then finally, the notation for the directional derivative is this. It's d sub u of f at p, which is 2, 0. So that's the directional derivative of f at p in the direction of u, and we just want del f dot u. Del f at p was 1, 2. U was 1 over root 5, 2 over root 5. So when we dot, we get 1 over root 5 plus 4 over root 5, which is 5 over root 5, and that's simply just root 5. So geometrically what we've done is we've taken a plane, a vertical plane that goes in the direction of V, and we've sliced the surface with that plane. It forms a curve, and at the point 2, 0, 3, the slope of the tangent to that curve is root 5. Okay, here are two important properties of the gradient. On this line here, I've written the directional derivative in terms of cosine theta, where theta is the angle between the gradient and the unit vector in question. And so you can see from that formula that that will be a maximum when cos theta is 1, and that's when theta is 0. So what that says is that the function f is increasing most rapidly in the direction of the gradient, and its value, the value of the directional derivative in that direction, is simply the length of the gradient. And then similarly, if theta is equal to pi, then we see that f is decreasing most rapidly in the opposite direction of the gradient, and the value of the directional derivative is negative the length of the gradient. So let me erase this and do an example with you. Find the max rate of change of this function at 2, 1. So we need what we're going to want. So we want the length of the gradient at 2, 1. That will be our answer. So let's start with the gradient. Okay, partial with respect to x. Think of this function as 4y to the 4th times x to the negative 1. So the partial with respect to x will be negative 4y to the 4th over x squared. And the partial with respect to y is simply 16y cubed over x. So del f at 2, 1, put 2 in for x, 1 in for y, and we're going to get negative 1, comma 8. So the length of del f at 2, 1 is the maximum rate of change in the function at that point. That's the square root of negative 1 squared plus 8 squared, which is root 65. Okay, and now a related problem, find the direction of the maximum rate of change of same function at the same point. So the direction of the maximum rate of change is simply del f at 2, 1. However, we want a unit vector, so we're going to have to divide out by its length. We've done all the work here. We know del f, and we know its length. So the vector we seek is negative 1 over root 65, comma 8 over root 65. So there's two answers here. One is a number, one is a vector. The number is the value of the directional derivative of f. It's the maximum rate of change at the point. The vector is the direction of the maximum rate of change of f. So if f is a surface up here, down here in the xy plane, if you're at a certain point and you want to know in which direction the function, so down here, in which direction should you point so that the function is increasing the most rapidly, you're going to go with the direction of the gradient. Okay, and that is related to this final topic, level curves. Recall level curves are curves on which the function is constant. And so the important thing here is that the gradient is normal to the level curves. Normal meaning orthogonal. So if you're looking at a topo map, the level curves are the curves on which the elevation is constant. Let's say you're climbing a mountain close to Exeter and you want to know which way to go up the mountain fastest. You're going to always point in the direction of the gradient. So let's take a look at an example. It's got two parts and I've already done one part. So we've got a function here. The first part is to find a level curve that passes through negative 5, negative 1. So what I did was I first found f of negative 5, negative 1. That's the c. That's the constant that you're going to set f of x equal to. And so once you find c, you set f equal to c. And then if I clean it up, I get this circle, x squared plus y squared is 26. So that's why you can see I've drawn the level curve in my picture as a circle there. All right, for part B, we want a unit tangent vector at P with positive x component. So the gradient we know will be orthogonal to the tangent, all right, because the gradient is orthogonal to the level curve. And so there'll be two unit tangents. One will point one way, the other will point the other way. We want the one with the positive x component. So in my picture, we're going to want this one. So the first thing we have to do is find the gradient. So del f at xy, okay, this is pretty easy. Up here, remember, I've got f. It's just going to be negative 1/2 x, and partial with respect to y is negative 1/2 y. Now we need del f at p. P is -5, -1. So we get 5/2, 1/2. Okay, there are two vectors, again, orthogonal to that vector. And you can use this fact over here to find them. It's super simple. Recall two vectors are orthogonal if their dot product is 0. So you can just quickly check that this vector and this vector both dot to 0 with this vector. All right, so two vectors orthogonal to del f are v1 equal to -1/2, 5/2, and v2 equal to +1/2, -5/2. Those are both orthogonal to the gradient. We want the one with the positive x component, so we want v2. However, we want a unit vector, so we need v2 divided by its length. So over here, we'll do a scrap. The length of v2 is the square root of 1/4 plus 25/4, which is the square root of 26/4, which is root 26/2. All right, so I'm going to take v2 and divide by its length. Its length is a fraction. So if I divide by root 26/2, that's the same as multiplying by 2 over root 26, the reciprocal. So 1/2, -5/2. Okay, and when I multiply that out, I get 1 over root 26, -5 over root 26. And that's my tangent vector. Okay, and that's the end of this section.